All right, let's get right into it. Welcome to this exclusive technical explainer. Today, we're focusing squarely on a domain where failure literally is not an option, mitigating risk in highly critical aerospace manufacturing. I'm stepping into the role of your lead process engineering consultant today, and we're going to meticulously break down the mechanics of machining the absolute most punishing materials on the planet. We are looking at the ultimate engineering crucible, that exact, unforgiving point where your machine tool, the cutting edge, and an S-grade superalloy collide. Listen, if you're an aerospace quality manager, a process engineering director, or running high-precision manufacturing, this is for you. We're zeroing in on the unique vulnerabilities hiding in your production line, and more importantly, how to engineer them out entirely.
So let's address the elephant in the room right off the bat. If you manage an aerospace machine shop, catastrophic tool failure and scrap structural components are your biggest daily nightmare. We are operating in zero-margin environments here. When you're machining complex, mission-critical components out of titanium or Inconel, the cost of a single scrapped part, it can easily spiral into the tens of thousands of dollars. And the primary culprit for this is usually catastrophic tool failure driven by extreme work hardening and totally unpredictable tool wear. Think about it. When a tool chips or chatters unexpectedly during a final finishing pass, it doesn't just cost you the physical tool. It costs you the workpiece, hours of machine time, and potentially your regulatory compliance. The financial and operational toll of that kind of unpredictability, it's just simply unacceptable.
Now, to understand exactly why this unpredictability happens, we've got to look at the physics inside the cutting zone. 1,300 degrees Celsius. Let that number sink in for a second. That is the staggering thermal load generated directly at the cutting edge when you push high-temperature S-grade alloys at optimal feed rates. At 1,300 degrees, standard cutting tools don't just wear down. Actually, it's worse. They undergo severe thermal degradation. Their core metallurgical structure actually begins to yield. If you can't effectively evacuate or withstand that immense heat, well, that energy transfers straight into your workpiece. The result? Severe work hardening, microcracking, and ultimately another rejected part for the scrap bin.
And it's specific materials that are triggering these massive thermal crises. We're talking about your nickel, cobalt, chromium, and iron-based superalloys. Now, obviously, these materials are chosen for jet engines and aerospace structures for a very good reason. They retain their extreme strength at wildly high temperatures. But that exact same property makes them an absolute nightmare to machine. Because they just don't soften easily under heat, they inherently trigger unpredictable vibrations, incredible kinetic resistance, and severe stress on the tool. To cut them successfully, you absolutely need solutions like polycrystalline cubic boron nitride, or PCBN cutters, which can actually maintain their hardness and structural integrity even while soaking in that 1,300-degree thermal bath.
Moving on to Section 1, the variable helix and coating innovation, engineering the antidote.
Okay, so here's the crucial question. How do we actually neutralize these extreme thermal and kinetic forces? Well, we can't change the laws of physics, right? And we certainly can't change the strict material properties required for aerospace components. So the tooling itself has to become our engineered antidote. Let's break down the anatomy of Evergreen's corner radius end mills. Your standard end mills often use a symmetrical flute design, but when you hit tough alloys, that symmetry creates harmonic resonance. Basically, the tool starts ringing like a tuning fork. That causes chatter, wrecks your surface finish, and leads to rapid tool death. So how do we stop the ringing? Evergreen engineers around this by using a specialized variable helix geometry. By varying the angle of the flutes, the tool actively disrupts those harmonic frequencies. You get superior vibration damping even during really aggressive cutting paths. You combine that with a maximized solid carbide core for extreme rigidity, and you've got a tool designed from the substrate up to actively suppress chatter before it ever reaches the workpiece.
But the physical geometry is really only half the battle here. Let's look at the surface level to see how we build our defense against that 1,300-degree heat. Evergreen utilizes advanced titanium silicon nitride, or TSIN, along with their specialized nanoblue coatings. Let me be clear, these aren't just paint. These are incredibly advanced molecularly bonded surface treatments. TSIN, in particular, gives you this phenomenal oxidation resistance and extreme surface hardness at highly elevated temperatures. It acts as a literal thermal barrier. It stops the intense heat of the chip from transferring down into the carbide core of the tool. By maintaining that crisp edge integrity under extreme thermal stress, these coatings are the absolute technological key to combating severe work hardening on your parts.
Which brings us to Section 2, Predictable Wear and Surface Integrity. Quality Control. Let's shift gears to the one metric that keeps every quality assurance director awake at night: predictable output.
In the aerospace sector, a tool that lasts a long time but fails unpredictably is infinitely worse than a tool with a shorter life that wears perfectly consistently every single time. The contrast on the shop floor is stark. With conventional tooling, you're looking at a highly volatile risk profile, unpredictable chatter, rapid thermal degradation right at the cutting edge, and inevitably, compromised structural integrity of your part. But when you switch to Evergreen's engineered corner radius mills, that variable helix and those thermal coatings work in tandem. They give you controlled, highly linear wear patterns. That means you're maintaining strict dimensional accuracy pass after pass after pass. You preserve the surface integrity of the component, and you keep your entire production line strictly within its Six Sigma quality parameters.
And it's important to note that this stability extends across their specialized range, too. For instance, when we look at polycrystalline diamond or PCD tooling, alongside their specialized non-standard milling cutters, we see a massive leap in processing dimensional stability. Because these PCD tools can comfortably reach a tool life of thousands, even tens of thousands of pieces without losing their edge geometry, they are exceptionally suited for machining those complex product outlines you deal with every day in aerospace. This level of rock-solid stability directly minimizes surface defects, it totally protects the delicate workpiece integrity, and it drives your scrap rates down to absolute minimums.
Let's move into Section 3, Aerospace-Grade Reliability, Mitigating Manufacturing Risk.
Let's take a step back and look at the macro-level impact this has on your entire manufacturing facility. Because at this level, we aren't just talking about cutting metal faster anymore. We are talking about risk management and strict regulatory compliance. When you're producing parts for jet turbines or landing gear, the FAA and other regulatory bodies require documented, repeatable perfection. Tooling predictability is the foundational layer of that aerospace-grade process reliability. Now, to prove that you do not have to sacrifice stability to achieve high throughput, let's walk through some specific cutting parameters from Evergreen's data on machining highly hardened steel. We're talking HRC 55 or higher. For finish machining, you can actually push speeds up to 200 meters per minute with a precise 0.3 millimeter knifing depth. Even in a high-efficiency, stable machining profile, you're maintaining a highly aggressive 150 meters per minute. And when you really need to remove bulk material under heavy cutting, you just drop the speed to 80 meters per minute, but you dramatically increase the depth of cut to around 2.0 millimeters. The takeaway here is profound, guys. With properly engineered carbide and PCB and substrates, high-efficiency cutting in the absolute hardest materials isn't a gamble. It's a perfectly stable, highly controlled process.
So, as we synthesize everything we've covered today, this quote perfectly encapsulates the entire philosophy. Engineered stability reduces variability in finishing, providing the risk mitigation and consistency required in highly regulated aerospace manufacturing. It is entirely about taking the chaos of a 1300-degree cutting zone and engineering it into a predictable, manageable data point. By leveraging those variable helix geometries, those thermally invincible coatings, and ultra-rigid carbide cores, Evergreen's precise engineering directly equates to process reliability. And for process engineering directors and quality assurance teams, that translates to the ultimate commodity: complete peace of mind.
We've explored the immense, real-world challenges of S-grade alloys and the precise technological solutions required to actually master them. Now it's time to audit your own shop floor. Are you still leaving your critical finishing passes up to chance with standard tooling, or are you ready to engineer absolute predictability into every single machining cycle? I strongly encourage you to optimize your tooling strategy, mitigate your production risk, and upgrade your high-temperature alloy machining protocols today. You can explore these dedicated, elite aerospace milling solutions over at www.evergreencarbide.com. The margins in aerospace are just too thin for unpredictable tools. So ask yourself, what will your next catastrophic tool failure cost you? And are you finally ready to engineer that risk out of your facility completely?